In mathematics, and more specifically in graph theory, a graph is a representation of a set of objects where some pairs of objects are connected by links. The interconnected objects are represented by mathematical abstractions called vertices, and the links that connect some pairs of vertices are called edges. Typically, a graph is depicted in diagrammatic form as a set of dots for the vertices, joined by lines or curves for the edges. Graphs are one of the objects of study in discrete mathematics. The edges may be directed or undirected. For example, if the vertices represent people at a party, and there is an edge between two people if they shake hands, then this is an undirected graph, because if person A shook hands with person B, then person B also shook hands with person A. In contrast, if there is an edge from person A to person B when person A knows of person B, then this graph is directed, because knowledge of someone is not necessarily a symmetric relation. This latter type of graph is called a directed graph and the edges are called directed edges or arcs. Vertices are also called nodes or points, and edges are also called arcs or lines. Graphs are the basic subject studied by graph theory. The word graph was first used in this sense by J. Sylvester in 1878. Definitions in graph theory vary. The following are some of the more basic ways of defining graphs and related mathematical structures. Graph, in the most common sense of the term, a graph is an ordered pair GI equals a, V, and E, comprising a set V of vertices or nodes together with a set E of edges or lines, which are two-element subsets of V. To avoid ambiguity, this type of graph may be described precisely as undirected and simple. Other senses of graph stem from different conceptions of the edge set. In one more generalized notion, E is a set together with a relation of incidence that associates with each edge two vertices. In another generalized notion, E is a multiset of unordered pairs of vertices. Many authors call this type of object a multigraph or pseudograph. All of these variants and others are described more fully below. The vertices belonging to an edge are called the ends, endpoints, or end vertices of the edge. A vertex may exist in a graph and not belong to an edge. V and E are usually taken to be finite, and many of the well-known results are not true for infinite graphs because many of the arguments fail in the infinite case. The order of the graph is: a graph size is the number of edges. The degree of a vertex is the number of edges that connect to it, where an edge that connects to the vertex at both ends is counted twice. For an edge U, AV, graph theorists usually use the somewhat shorter notation of adjacency relation. The edges E of an undirected graph G induce a symmetric binary relation on V that is called the adjacency relation of G specifically. For each edge U, AV the vertices U and V are said to be adjacent to one another, which is denoted way AV. Types of graphs, distinction in terms of the main definition, as stated above. In different contexts it may be useful to define the term graph with different degrees of generality. Whenever it is necessary to draw strict distinction, the following terms are used. Most commonly, in modern texts in graph theory, unless stated otherwise, graph means undirected simple finite graph. Undirected graph: an undirected graph is one in which edges have no orientation. The edge is identical to the edge, that is, they are not ordered pairs, but sets U, AV of vertices. The maximum number of edges in an undirected graph without a self-loop is n, 1/2. Directed graph. A directed graph or digraph is an ordered pair DA equals a, B, A, with VA set whose elements are called vertices or nodes, and A set of ordered pairs of vertices, called arcs, directed edges, or arrows. An arc Y equals A, X, AY, is considered to be directed from X to Y. Y is called the head and X is called the tail of the arc. Y is said to be a direct successor of X, and X is said to be a direct predecessor of Y. If a path leads from X to Y, then Y is said to be a successor of X and reachable from X, and X is said to be a predecessor of Y. The arc is called the arc inverted. A directed graph D is called symmetric if, for every arc in D, the corresponding inverted arc also belongs to DA's symmetric loopless directed graph DA equals a, B, and A, is equivalent to a simple undirected graph GI equals a, B, and E, where the pairs of inverse arcs in A correspond one-to-one with the edges in E. Thus the edges in G number E equals A/2, or half the number of arcs in D. A variation on this definition is the oriented graph, in which at most one of and maybe arcs. Mixed graph. A mixed graph G is a graph in which some edges may be directed and some may be undirected. It is written as an ordered triple GA equals a, B, and E, and A, with B, E, and A defined as above. Directed and undirected graphs are special cases. Multigraph. A loop is an edge which starts and ends on the same vertex. These may be permitted or not permitted according to the application. In this context, an edge with two different ends is called a link. The term multigraph is generally understood to mean that multiple edges are allowed. Where graphs are defined so as to allow loops and multiple edges, a multigraph is often defined to mean a graph without loops. However, where graphs are defined so as to disallow loops and multiple edges, the term is often defined to mean a graph, which can have both multiple edges and loops, although many use the term pseudograph for this meaning. Quiver. A quiver or multidigraph is a directed graph which may have more than one arrow from a given source to a given target. A quiver may also have directed loops in it. Simple graph. As opposed to a multigraph, a simple graph is an undirected graph that has no loops and no more than one edge between any two different vertices. In a simple graph the edges of the graph form a set and each edge is a distinct pair of vertices. In a simple graph with n vertices every vertex has a degree that is less than n. Weighted graph. A graph is a weighted graph if a number is assigned to each edge. Such weights might represent, for example, costs, lengths or capacities, etc. depending on the problem at hand. Some authors call such a graph a network. Weighted correlation networks can be defined by soft thresholding the pairwise correlations among variables. Half edges, loose edges. In certain situations it can be helpful to allow edges with only one end, called half edges, or no ends. See for example signed graphs and biased graphs. Important graph classes. Regular graph. A regular graph is a graph where each vertex has the same number of neighbors, that is, every vertex has the same degree or valency. A regular graph with vertices of degree k is called a car-regular graph or regular graph of degree k. Complete graph. Complete graphs have the feature that each pair of vertices has an edge connecting them. Finite and infinite graphs. A finite graph is a graph GI equals a, B, and E, such that V and E are finite sets. An infinite graph is one with an infinite set of vertices or edges or both. Most commonly in graph theory it is implied that the graphs discussed are finite. If the graphs are infinite, that is usually specifically stated. Graph classes in terms of connectivity. In an undirected graph G, two vertices U and V are called connected if G contains a path from U to V. Otherwise, they are called disconnected. A graph is called connected if every pair of distinct vertices in the graph is connected. Otherwise, it is called disconnected. A graph is called k-vertex connected or k-edge connected if no set of k1 vertices exists that, when removed, disconnects the graph. A k-vertex connected graph is often called simply k-connected. A directed graph is called weakly connected if replacing all of its directed edges with undirected edges produces a connected graph. It is strongly connected or strong if it contains a directed path from U to V and a directed path from V to U for every pair of vertices U, AV. Category of all graphs. The category of all graphs is the slice category whereas the functor taking a set to. Properties of graphs. Two edges of a graph are called adjacent if they share a common vertex. Two arrows of a directed graph are called consecutive if the head of the first one is at the tail of the second one. Similarly, two vertices are called adjacent if they share a common edge, in which case the common edge is said to join the two vertices. An edge and a vertex on that edge are called incident. The graph with only one vertex and no edges is called the trivial graph. A graph with only vertices and no edges is known as an edgeless graph. The graph with no vertices and no edges is sometimes called the null graph or empty graph, but the terminology is not consistent and not all mathematicians allow this object. In a weighted graph or digraph, each edge is associated with some value, variously called its cost, weight, length or other term depending on the application. Such graphs arise in many contexts, for example in optimal routing problems such as the traveling salesman problem. Normally, the vertices of a graph, by their nature as elements of a set, are distinguishable. This kind of graph may be called vertex-labeled. However, for many questions it is better to treat vertices as indistinguishable. Then the graph may be called unlabeled. The same remarks apply to edges, so graphs with labeled edges are called edge-labeled graphs. Graphs with labels attached to edges or vertices are more generally designated as labeled. Consequently, graphs in which vertices are indistinguishable and edges are indistinguishable are called unlabeled. Examples. The diagram at right is a graphic representation of the following graph: V equals 1, 2, 3, 4, 5, 6, E equals 1, A2, 1, A5, 2, A3, 2, A5, 3, A4, 4, A5, 4, A6. In category theory, a small category can be represented by a directed multigraph in which the objects of the category represented as vertices and the morphisms as directed edges. Then, the functors between categories induce some, but not necessarily all, of the digraph morphisms of the graph. In computer science, directed graphs are used to represent knowledge, finite state machines, and many other discrete structures. A binary relation or on a set X defines a directed graph. An element X of X is a direct predecessor of an element Y of X if X are Y. A directed edge can model information networks such as Twitter, with one user following another. Important graphs, basic examples are, in a complete graph, each pair of vertices is joined by an edge. That is, the graph contains all possible edges. In a bipartite graph, the vertex set can be partitioned into two sets, W and X, so that no two vertices in W are adjacent and no two vertices in X are adjacent. Alternatively, it is a graph with a chromatic number of 2. In a complete bipartite graph, the vertex set is the union of two disjoint sets, W and X, so that every vertex in W is adjacent to every vertex in X but there are no edges within W or X. In a linear graph or path graph of length n, the vertices can be listed in order, VO, V1, Vn, so that the edges are via 1 for each I equals 1, 2, n. If a linear graph occurs as a subgraph of another graph, it is a path in that graph. In a cycle graph of length n A perm L3n, vertices can be named V1, Vn so that the edges are via 1 for each I equals 2. And in addition to Vn V1. Cycle graphs can be characterized as connected to regular graphs. If a cycle graph occurs as a subgraph of another graph, it is a cycle or circuit in that graph. A planar graph is a graph whose vertices and edges can be drawn in a plane such that no two of the edges intersect. A tree is a connected graph with no cycles. A forest is a graph with no cycles. More advanced kinds of graphs are the Peterson graph and its generalizations, perfect graphs, K-graphs, caudal graphs, other graphs with large automorphism groups, vertex transitive, arc transitive, and distance transitive graphs. Strongly regular graphs and their generalization distance regular graphs. Operations on graphs. There are several operations that produce new graphs from old ones, which might be classified into the following categories: elementary operations, sometimes called editing operations on graphs, which create a new graph from the original one by a simple, local change, such as addition or deletion of a vertex or an edge, merging and splitting of vertices, etc. Graph rewrite operations replacing the occurrence of some pattern graph within the host graph by an instance of the corresponding replacement graph. Unary operations, which create a significantly new graph from the old one. Examples: line graph, dual graph, complement graph. Binary operations, which create new graph from two initial graphs. Examples: disjoint union of graphs, Cartesian product of graphs, tensor product of graphs, strong product of graphs, lexicographic product of graphs. Generalizations: in a hypergraph, an edge can join more than two vertices. An undirected graph can be seen as a simplicial complex consisting of one simplices and zero simplices. As such, complexes are generalizations of graphs since they allow for higher dimensional simplices. Every graph gives rise to a matroid. In model theory, a graph is just a structure. But in that case, there is no limitation on the number of edges, it can be any cardinal number, see continuous graph. In computational biology, power graph analysis introduces power graphs as an alternative representation of undirected graphs. In geographic information systems, geometric networks are closely modeled after graphs, and borrow many concepts from graph theory to perform spatial analysis on road networks or utility grids. See also, dual graph, glossary of graph theory, hypergraph, graph, graph database, graph drawing, graph theory publications, list of graph theory topics, network theory, Bayesian network, web graph, conceptual graph, SageMath, Network X, Mathematica, Graph Theory, Notes. References: Balakrishnan, V.K. Graph Theory. McGraw-Hill. ISBN A0-07-005489-4. Berge, Claude. Thar Copyright Everyday Graphs Aces Applications. Dunod, Paris, Collection Universitaire de Maths Copyright Matix, 2. pp of plus 277. A translation. Dover, New York, Wiley. 2001, 1962, Biggs, Norman. Algebraic Graph Theory. Cambridge University Press. ISBN A0-521-45897-8. Boloba S., Bar Copyright La. Modern Graph Theory. Springer. ISBN A0-387-98488-7. Bang Jensen, J. Gutin, G. Digraphs, Theory, Algorithms and Applications. Springer, Diestel, Reinhard. Graph Theory. Berlin, New York, Springer Verlag. ISBN A978-3-540-26183-4A. Graham, R.L., Graph Paragraph Chal, M., and Lover S. ed., L., ed. Handbook of Combinatorics. MIT Press. ISBN A0-262-07169-X. Gross, Jonathan L. Yellen, J. Graph Theory and Its Applications. CRC Press. ISBN A0-8493-3982-0. Gross, Jonathan L., and Yellen, J., ed. Handbook of Graph Theory. CRC. ISBN A1-58488-090-2. Harari, Frank. Graph Theory. Addison Wesley Publishing Company. ISBN A0-201-41033-8. Iyanaga, Shakichi. Kawada, Yukiyoshi. Encyclopedic Dictionary of Mathematics. MIT Press. ISBN A0-262-09016-3. Zwillinger, Daniel. CRC Standard Mathematical Tables and Formulae. Chapman and Hall CRC. ISBN A1-58488-291-3. Further reading, Trudeau, Richard J. Introduction to Graph Theory. New York, Dover Publications. ISBN A978-0-486-67870-2. Retrieved August 8, 2012. External links: Weierstein, Eric W., Graph, MathWorld.